Okay, hello. I said I'd start on time, so it's 2 o'clock. I think this is probably about as many people as we can fit in anyway. Thanks all for coming. Hopefully this will be useful. I am hopefully recording this, so people who can't make it can watch it later, if it works. So the format of this is kind of alternating slides and practical stuff. The exercises are quite short. They don't build on each other, so I'm going to probably give you like 5 minutes for each one. If you don't quite get to the end, we'll probably have to move on anyway, because we've got a lot of stuff to go through in 2 hours. I guess I shall start. So what am I going to cover? First of all, a bit about background about what Git is, why it's different from Subversion or other source control systems you may have seen. Some basics of how to use it for simple stuff. Precision staging doesn't make much sense until I've explained what staging means. I'm going to talk a bit about branching, a bit about tags, something about the internals of how Git actually works. Just a very small amount. You don't really need to know it, but it's useful to kind of understand what's happening when you're using Git repositories. A bit about merging and rebasing, which is always fun. Distributed Git. Patch is an email you probably won't use very often, but it's handy to know how to do occasionally. A bit about some ways different teams work with shared projects using Git. How to set up hooks. How to rewrite history. Make all the Subversion people go, ugh. How to hopefully fix some common things that are likely to go wrong, or at least where to look to find out how to fix things. And that's it. I think I just said all those things before I clicked on them, didn't I? Sorry. I'll look at the other slide this time. So, part one, some background about Git, where it came from, what the commands are. So, very early version control, at some point people thought, well, hang on, we can't just have a bunch of files lying around and stored in zip files and directories and what have you. So, people started doing version control locally, just some kind of version database on the machine they're working on. For quite a long time now, most people have used server-based version control, so things like RCS, CVS, Subversion, obviously, where you have your version database all lives on a server somewhere, and you just check out a working copy. Git is different, along with other things like Mercurial and Bazaar. There's a few other ones in that it's distributed. So to sort of explain that, we go back to the kind of single local repository thing, and then imagine that several people all have the same single revision control, and they all talk to each other, and they can also talk to one on a server if you want to. So everyone has a copy of the whole revision control history on their local machine. I'm guessing most people know, at least the basics of this already. With Git, there's one slight extra oddity which can confuse people, so I'll mention it now. Something called the staging area, or the index. So you have your working copy of your files, the ones you're actually developing, whatever. You have your repository with all the history in, and then you have the index, which is kind of where the files go through, or where the changes go through on their way to being committed, which allows you to make kind of more finely grained commits than you would be able to do with some other systems. That will make more sense. We come back to it in one of the exercises later. So commands that Git provides, there are quite a lot of them. Most of them you're never going to use, probably not even going to see. Git is built up of 2 layers. They're called the porcelain and the plumbing. The plumbing commands are all the things that make it work under the scenes. If you want to, you can use them directly, but you very rarely need to. And then the plumbing is another bunch of commands that talk to the porcelain, other way around. Porcelain commands talk to the plumbing, and they expose it in a more user-friendly fashion. So if we remove all the plumbing commands, there's still quite a few, but nowhere near as many as there were. And of those, you'll probably find that most of them you won't need. So I think there's probably a dozen or so that you're likely to use day to day. Okay, so what do we actually do with it? So absolute basics of Git. Just out of interest, how many people have used Git before? About half-ish? Okay. So this is going to be fairly obvious to you guys. The first thing you need to do if you're using Git is create a new repository. It's much easier than with something like Subversion because it is on your local machine. You basically run git init in the directory that your files are in, and that's it. You've got a Git repository ready to go. So once you've got your repository, the first thing you're likely to want to do is add a file to it. So imagine we're in this repository. We've got one file that's got some changes in it. So we do git status to tell us what the state of the repository is, and tells us we've got one untracked file, foo.txt. You notice that it says things like use git add file. The status commands and lots of things in Git are actually quite helpful in that they'll tell you what command to run to do certain things. So it's worth actually reading those if you're not sure what's going on. So this quite clearly tells us use git add file to include it. So we go ahead and say git add foo.txt, and then we run git status again. And now it tells us changes to committed, new file. So this file, remember I talked about the index a minute ago? This file is now in the index, but it's not in the repository yet. It's not actually checked in or versioned. So now we've added it, we can commit it. So we say git commit, and the -m means use this message as the commit message. If you don't do -m, it'll pop up an editor, and you type your message in. And it commits it, tells us what's changed, added a new file. So now let's say we've changed a file. So we'll do git status again. Now it's not telling us there's any new files, it just says changes not staged. So this is a change that's in your working copy, it's not in the index, and it's not in the repository. Again, it tells us use git add or git commit -a to commit it. So we want to see what the differences are. So we run git diff, and there's a bunch of lorem ipsum text, latecomers, and it tells us that one line in that text has changed, which is presumably what we want to commit. So again, we'll just say git add, so add those changes to the index. Once again, we'll do git status, it just tells us it's modified, and again git commit with a message, and it tells us that one file's changed. So going back to that picture we had with the index and the staging area and everything, so those commands on the left, add, remove, move, those are the commands that affect the index. So adding a new file, adding some changes, removing a file completely from the repository or from the current version, the history is obviously still there, and renaming a file, MV, same as in Unix. All those work on the index, and once you've done them they all have to be committed. And then commit takes all the changes that you've got staged in the index and creates a new version in the repository. So how do we see what's in the repository? Unsurprisingly, with git log. You can see here it lists some commits, it tells you who changed them, and it gives you the commit messages. You can specify all sorts of different formats for git log to tell it what you want to see. Also notice the yellow lines where it says commit. For people who use Subversion, version numbers 1, 2, 3, 4, whatever. Git uses SHA hashes. The reason for that will become slightly clearer later, but you can't rely on things just being numbered. Git history is not kind of as simple as that anyway. Each commit has a unique SHA, basically. That's all you need to know to reference it. If we want to see what happened in one of those commits, we can do git show, and it gives us the log stuff at the top, and then a kind of a diff of what changed in that commit. If multiple files, it will just keep paging up until you get to the end of it. If you don't want to see quite that much detail, you can say git show --stats, and it will just tell you, yeah, foo.txt has changed. It's had 2 lines. Well, I think 2 plus minus means 2 lines added and 2 lines removed. Or, sorry, 1 of each for the look at it. If you want to see even less detail, so that obviously you'd get 1 line per file in the commit. Even less detail, you can say short stat, and that will literally just tell you how many files were changed in that commit. So comparing different versions, if you just want to see what's changed locally, what your uncommitted changes are, just a simple git diff will show you the diff as you'd expect. If you've already git added some changes and you want to see the change between those and the repository to make sure you're about to commit the right thing, then git diff --, sorry, ignore that. Yep, that's not what I expected to say. If you do want to do that thing, and if I'd written the right thing on the slide, you say git diff --, cached, and it will tell you the difference between the staging area and the repository, rather than between your working copy and the staging area. You can also give it any arbitrary points that you want to diff between. So in this case, we pick 2 commits and say what's changed between that commit and that commit. When we get onto branches later, you can do the same thing between branches, tags, whatever you like. One last thing to mention that's quite handy with git log is something called the pickaxe. And I believe it's called a pickaxe because the -s, if you kind of squint, maybe looks a bit like a pickaxe. What that does is it searches for changes that introduced or removed a particular bit of text. So in this case, we added a line which had the word Expelliarmus in it, amongst some load of other spells. And we just say we've just got a bug report and says this word appeared, or when did I introduce the class called such and such. Then you can just git log -s, some string, and it will tell you all the commits that introduce any change with that word in. So in this case, it will just tell us that one commit where we added that line. If you want to find out who broke stuff, then git blame, same as Subversion blame for the Subversion users. I don't think Git's as polite as Subversion. It doesn't alias to praise like Subversion does. Git blame just prints out the file you give it, and it annotates it along the left with the commit and the author. It's almost always me, I find, if I'm trying to find out who broke something. Okay, so I briefly mentioned that you can pop up an editor when you're doing a commit. You don't have to just do a one-line message. There's kind of a convention in Git for commit messages, which is that you have a subject which is one short line. So in this example, a note about good messages. So that's what will appear if you're just doing a quick git log. If you need to add more information, then you add a blank line. Sorry, before I say that, it's traditional to say add note, add file, change something, not added, changed. I guess that goes back to Linux when Git was first created. You then put a blank line and then as much text as you want to describe what the change was. And there are various reasons for doing that. Some of the tools expect a subject and then more stuff. Git can also integrate with email, and it'll use that as a subject of an email. And it's just sort of generally good practice to get decent commit history. So that's enough of me waffling for now. If you go to exercise 1 in the exercises that I sent out, I'll give you about 5 minutes. It's basically just play around with Git. There's a README file that will explain what to do. Just give it a go and see how you get on. Okay, everyone kind of got everything set up and working more or less? I'm going to have to push on, otherwise I don't think we're going to get through. The next thing I was going to cover was more fine-grained control of staging, so adding files to the index. So when you do a git add, you don't just have to say add this file. You can only add part of the file. So here we're doing a git diff, and you see there's 2 separate changes to one file. If we now say git add minus, sorry, go back one. Or 3. Right, if you say git add minus p for patch and the file name, the first thing it does is prints effectively the diff. It says there's a chunk of changes. Do you want to stage this hunk? And it gives you a whole bunch of options. If you hit question mark, it'll explain what those options mean. In this case, we only want to submit one of those changes, not both of them. So we'll say S for split. and it says split into two, and now it just shows us the first one. It says, do you want to add that one or not? And we'll say, yeah, go on, we'll add the first one. And then now it shows the second one. It says, do you want to add that one? And we'll say no. Then now if we run git status, we'll see that file appear on both of those lists. So the file is modified and changed staged to be committed, and it's also modified and not staged. So this is where that index comes in useful. It means you can do things like this. You can have some changes that you're actually committing and some you're not. This is probably not something you want to do too often. You want to try and commit things all in one go so that you know they work, but it's handy to know. If you want to have even more control, you can say, sorry, if we just do a git status, now we've got one modified file and one new file. And we want to, so this could be a whole bunch of files. We only want to add some of them. We can say git add -i for interactive, and it now gives us this great menu of options. So the first thing we're going to say is we want to add an untracked file. So we'll hit A for add untracked. It gives us a list of the files. In this case, there's only one of them, so we hit 1. It puts a little asterisk next to it to tell us that one's selected. If there are other ones, they'd be listed without the asterisk. And then we just hit return to tell it that that we're done, and takes us back to the menu. And now let's say, as well as adding that file, we wanted to add half of the change from the first one. So we'll say patch. We could have just said update, which would have taken a whole file update. So patch now takes us into, sorry, status first. So we did a status that says, right, we've now got, so you can see where we've got these two columns, staged and unstaged. So the new file we added, bar.txt, there's nothing unstaged, and there's a change in the staged section. The other file we haven't touched yet, so it's nothing staged and 5 new lines unstaged. So now we'll say patch. Again, we'll pick the file to change. Then we'll hit return, and then it drops us into a patch exactly the same as we just saw for git add -p. And we can do exactly the same thing, which I'll whiz through as fast as Keynote will let me. And then we're back to our main menu again, and we say status. Now tells us that there's various things staged. Now we're all done, so we'll just say quit. And now if we look at git status, we'll see the new file's ready for commit. One of the changes to the changed file is ready, and the other one, just like with the git add -p, isn't ready for commit. And now you can just do a git commit, and that's what'll go in. So hopefully that'll make more sense if you actually try it yourself. So if you look at exercise 2, that basically will give you a chance to try out the interactive add. Okay, so I'm afraid those of you who haven't finished, you can do it for homework or something. So we're going to move on to branches, which are probably more useful, to be honest, anyway. Also gives me the opportunity to put my standard cat picture that I always get into every presentation. So creating a branch in Git is as simple as git checkout -b, and then the name of the branch that you want to create. If you don't want to create the branch from where you currently are, so generally that would be at the head of master, you can pick a commit. So in this case we pick the commit with that abbreviated char, and just say git checkout -b new branch from that point, and that could be a branch name or anything. So that thing there is a commit-ish reference, what Git calls it. There's a whole bunch of different ways you can refer to commits. So you can use the full char or part of the char, so that massive great long string. Generally you'd only use that if you were just double clicking and pasting. No one's going to type it out. You can abbreviate it. If you give it at least 4 characters, as long as they're unique, it'll use that. So you can go all the way down to that. You can also give it the name of a branch or a tag, which we'll mention later, or the current head, which is where you are in the current branch. So we could say git checkout master, the name of a branch, some tag that you've created. Head is like a special pointer that just points to where you currently are in the repository. You can also use ancestors of commits. So if you put a tilde on the end, that means one commit before that one, and that you can add to any of the other types of reference. If you put multiple tildes, it means keep going back. You can also just put a number, so those last two are equivalent. So 3 commits before the current master. When we cover merges, we'll discover that commits can have more than one parent. So the caret means the parent of a merge commit. You probably won't need to use it other than be aware that it exists. If you use that for a normal parent, it will work most of the time. And then if you happen to use a merge commit, it'll behave differently. Because if you say the second parent with a caret, that means for a merge commit that has 2 parents, it's the second one across, not going back 2 like you would with a tilde. And you can combine those. I've never had to do that, but you might come across it. If you've got a branch you want to get rid of, simple git branch minus d. If you do it with a branch that's not merged into the current branch, it'll tell you. But it does tell you how to do it if you're really sure that you want to get rid of it. Just use a capital D, and then it will just throw it away. You'll notice it says what the SHA was of that branch. You might wonder why that's useful. It turns out it doesn't actually delete it, as we'll see later. So, more exercises. I think we're up to exercise 3. Have a quick play with some branches. Okay, moving on to tags. So tags are basically just pointers to commits, just to make it easy to find things. So it might be a latest release, or where a particular bug was found, or whatever you want. Anything you just want an easy readable label attached to a commit. So to create a tag, unsurprisingly, git tag and then the name of the tag. If you then try and create the same name tag and point it to a specific commit or a different commit, so if you say git tag something with no arguments, it'll just point to the current, wherever your current head is. So now we're trying to effectively move that tag, and it will tell us that it can't move it. This is one of the cases where it doesn't actually tell you what to do about it, but the answer is git tag minus F to force it. If you're really sure you want to move that tag, not always a good idea to move tags around, but they are, by default, they're local. You have to push them onto the server. And as with all these things, git help tag will tell you what all the options are. If you want to delete a tag, again, as simple as git tag minus D. That was the shortest section ever. Exercise 4. Okay, there seems to be a few people sitting around, so I'm hoping most people got a fair way through that. So I said earlier I was going to just briefly go into how Git stores stuff internally. Again, you don't need to know this, but it kind of makes some things make more sense, I think, if you do know it. Particularly if you use things like Subversion, which I think kind of stores diffs. So a commit is basically a diff from the previous one. Git doesn't work like that at all, so it can get very confusing if you think of it as a commit being a diff from the previous commit. So how does it store it? This is the structure of a brand new Git repository. So when you do Git init, this is what gets created. The bits we're interested in really is the objects directory and the refs directory. Refs is just where Git stores pointers for things, so where branches point to, where tags point to, are just created as simple files under there, that just so it knows which commit master is currently pointing at, and so on. Inside objects, there are 3 types of thing that Git stores. The first one is blobs. A blob is literally just a chunk of content, so text or binary files, just literally the data. It doesn't have any metadata, it doesn't have a file name associated with it, so when we committed a text file, the literal text contents of that file would have been saved in a blob in the objects directory with its own SHA, not a commit SHA, just literally the result of doing a SHA hash on that content. So if you commit 2 files with exactly the same content in any Git repository in the world, they will always have the same SHA because it's literally just a hash of the content of the file. And that makes it easy for Git to kind of optimize things when you've got, let's say, lots of branches all pointing at much of the same content. So that's how it stores the actual content, but obviously it needs to also keep track of what that content represents, where it lives in the file system. So the second type of object is a tree. A tree kind of is like a directory. So it points to a number of objects. So at the bottom level, when you've got a single file, there'll be a tree that just has one blob as a child of it. And that tree has contains stuff like the file name, the permissions, so that when you do a git checkout, it knows where to put that blob on your file system. The third type of object is a commit, and the commits are the things that obviously you've been creating when you're committing changes. And a commit it has the data about who did it, when they did it, and then it contains a pointer to I think a single tree, potentially also points to its parents. So you've committed a change, obviously that's committed on top of the previous commit. So a commit knows what its parents are, who did it, and the tree representing the repository structure at that point. So in a big repository, that tree is going to have lots of other trees underneath it, and then blobs representing files at various points. And because it's using hashes to represent the blobs, if you've got, let's say, 10 branches in your repository and 100 commits on each branch, if 99% of the files haven't changed, they're still represented by a single blob in the repository because the SHA is the same. And that's how it manages to do really cheap branching without using up all your disk, because it'll only go down until it reaches the point where the tree is identical to a tree in a previous commit, and then it doesn't have to do anymore because that tree has the same SHA, so it's the same tree. I'm not sure how much sense that made. Don't worry too much about it. You'll get a chance to play with it in a second. The other thing I wanted to mention is garbage collection. So what I've just described assumes that all these objects are all just unpacked in the file system. You can run git gc and it will compress stuff. It also does that for you sometimes when it feels like it. Often if you're doing a git push to send to a remote repository, it'll pack stuff up before it sends it to save bandwidth. And what that does is it takes all the various bits and pieces in the repository and it compresses them somehow and sticks them in a binary file called a pack file. So after we've done that, if we look at the object's pack directory, which was previously empty, it now has an index and a pack file. That index lists all the previous objects that used to be loose in the objects directory, and the pack file is just some opaque binary format that Git uses to store those. So that's how it kind of gets stuff that doesn't change much or whatever can be compressed into there. Again, you don't need to know any of that to be able to use Git, but it's handy to know what happens. So there's another exercise. This time you're not doing any commits or anything. Exercise 5, I think we're on. Basically just have a look at one of the other repositories and just have a poke around in that directory and see what you find. There's some commands in the README that explain how to look at the objects. Okay, so moving on to merging and rebasing. Now, the reason I ended up doing this Git Masterclass was that when we ran the boot camp for the grads, we made everyone use Git, and lots of problems came up with merge conflicts and things. And I somehow managed to volunteer to try and explain a bit more about how it's supposed to work. So merging and rebasing is generally the bit where things go wrong. So I'm going to explain the various types of merge that you can do in Git, and then in the exercise you get to have a quick go at all of them and compare what comes out. So imagine we've got a repository that's got a master branch and a branch called branch. They've diverged. There's 2 different commits on each branch, and we want to merge the branch into master. So the simplest way is we check out the master branch and we just say merge branch. And what that does is it creates a merge commit, which is a special type of commit that has multiple parents. So I mentioned before about the caret thing for pointing to multiple parents. So if there are no conflicts, that commit will literally just be a commit with the commit, who did it when, and parents of, in this case, D and F. If there are merge conflicts, it may also have changes in it, like a normal commit. So yeah, that's the simple merge. Generally, that's not always the best way of doing it. And I should have mentioned it also moves the master pointer effectively onto that merge commit. So that's now the latest change. So it's worth noticing now, if we were to remove the branch, all those commits are still there. E and F that were on the branch are now also on master. So C and D are on master, E and F are also on master. It doesn't have a linear history anymore. Unlike Subversion, a single Git branch can branch internally to sort of an arbitrary degree of complexity. Usually it's a good idea to try and avoid that, because if you're trying to work out when you broke something or something like that, you can't just step back, because which way do you go? So a slightly simpler case, imagine now we've done 2 commits on the branch, but there's been no changes on master. So we do exactly the same thing. We'll check out master, and we'll merge the branch. And in this case, Git's clever enough to think, oh, well, I don't need to do anything, I don't need to do a proper merge here, because it's just a linear thing. So it fast forwards the master pointer straight onto the end of the branch, and effectively you end up with just a simple linear history. If you don't want it to do that, you can do the same thing, git checkout minus master. So in this case, let's say on our branch we had a whole bunch of little fiddly commits, like added failing test for this, made the test pass, did something, it didn't work, did some more stuff. But on our master branch, we just want one nice clean commit that says added this feature. So what we can do is say git merge minus squash. And what that does is it creates a brand new commit on master, which contains all of the changes in those other commits. In fact, that's not strictly true. What it does is it applies all those other commits to your working copy, and to your staging area, but doesn't commit them. After you've done the merge minus squash, you still have to say git commit. By default, if you don't give it a message, it will pop up an editor with all the other commit messages in, and then you decide what you want to put in the message. So you now have a totally separate commit. If you were to delete the branch, the things on the branch would go away on the basis that presumably they were temporary things that you didn't want anymore. Another way you can do a merge is in the same situation. Let's say we do want to keep those little changes on the branch, but we want to make it obvious that that was a branch and give the kind of resulting commit a name. So we can do git checkout master, and when we do our git merge, we'll say no fast forward. So even though Git can clearly see that it could fast forward it, we're telling it it's not allowed to. In that case, it'll do what it would have done in the first case, which was create a merge commit. So now we have kind of a best of both worlds in some ways. So we can see our master kind of goes along. Our commit E would be the one that says added cool new feature, but we can see the individual fiddly history underneath. So that's the way a lot of people tend to do merge commits. The other way of doing it, another way of doing it. So going back to our case where we have got a conflict. So what we want to do now is we want to merge the branch on top of master, but we don't want any merge commits. We just want a nice simple linear master. So we go onto our branch this time, and we say rebase onto master. Now what rebase does is it kind of recreates the current branch as if it were on top of the thing you pointed at. So the first thing it does is it takes the branch pointer and moves it to master. So it resets it to point to the thing that you're rebasing against and kind of keeps hold of the commits somewhere. And then it goes through all those commits one at a time, and it effectively patches them on top of of where it is. So we end up with the equivalent of commits E and F. If this were something like Subversion, they would be the same commits because they'd be diffs. Don't forget, in Git, a commit is just a pointer to a bunch of files. So those commits aren't the same because they've got different parents, different times, whatever. So you are kind of breaking the history. You're throwing away commits and creating new ones. If there are merge conflicts, you'll have to fix them. You'll end up with slight differences because of that. But once it's finished, it moves the branch up to the end. So now all your changes on your branch, all being well, are now as if they'd been done after the work that had already been done on master. At that point, you can then go and check out master, and now you can do a merge, and it's the opposite of the no fast forward. We say only fast forward. Basically, you're telling it, if I've left this in a state where you can't just fast forward, then fail the merge. And now it just moves master on, and we've got a nice linear history with all the individual commits again. That looks like the same slide to me. So another mystery merge. I'm just waiting to find out what it's going to be. Okay, so let's say this isn't quite a merge. I just threw it in because it's sort of related. Let's say we've been working on the branch. Actually, we've realised that was a complete waste of time. We've done something we didn't need to do. But for some reason, we want commit E. So commit E has got something useful. F, yeah, silly idea. Forget about that. And commit E could come from anywhere, not necessarily just from a branch. So Git has a thing called cherry pick that basically means take that commit from wherever it is and try and stick it on top of where I currently am. And like rebase, that creates a new commit that replicates the one you've cherry picked. You may have merge conflicts to fix, but so that's kind of useful if you've got parallel branches for, let's say you're fixing live issues in one branch and you're working on the next release in another branch. If you have to do an emergency bug fix, you can cherry pick it across into your master branch. So that was a lot of pictures of merging. Basically, the exercise is to kind of go through most of those again. There's like 4 or 5 copies of identical repos for you to play with. So have a go with those. Okay, I think we'll move on. So we've looked at merging and branching within a single repository. Obviously, Git is a distributed version control system. We should probably mention the distributed bit at some point, and that point is now. So I guess most people, the first experience they will have had of Git would have been going to GitHub and doing git clone of some repository. So you'll recognize this kind of command, git clone, and then a URL or a file name. By default, it just picks the same name. You can also give it a destination directory as well. So that URL can be over SSH, it can be over HTTP, HTTPS, and it can be on the local file system. And there's also the Git protocol, which is probably less used now. I think most things tend to use SSH. And that just goes off to a remote repository, and it just drags down the entire copy of the entire repo. So it's not like the version where you're just checking out the latest version. You're getting all the history. If you then unplug your network, you've still got access to the whole repo, all the branches. So if you then were to go into that repository that you've cloned and say git branch -a, I know at least one person was asking how you get a list of the branches earlier, and just git branch. Git branch -a means also show me remote branches. So you can see we've got one local branch, which is master, which it will have set up to track the origin master. And then by default, when you clone a repo, it sets up a remote called origin, and it says, these are all the branches that were in that project. Now, it's important to recognize the difference, but what these are pointing at isn't the remote repository. This is pointing to your copy. So you have your remote directory locally contains you can have multiple different repositories that you're pointing to, and it maintains a copy of all of those. So when you do git log origin master in your local repository, it's doing a log of your local copy of origin master. If you haven't fetched from the network recently, you won't see any new commits, but it will work if you're not connected to the network. So might make more sense with pictures. So when you do a git clone, you're going off to a server or another directory, and you're saying, give me a copy of all your branches and all the history for those. So the first thing it does is it sets up a remote pointer in your repository that says, I know about a remote Git repository and I'm going to call it origin. You can create multiple ones called different things if you want to, pointing to different repositories. And then I'm going to create local copies of the branches. And bearing in mind, all these are just trees and blobs and commits, the same as your local ones. And then what it also does is it, by default, will check out the master branch of the repository you've cloned. I think there's an option to tell it not to do that. All these commands have got a billion options, which you can dig around in the documentation for. And finally, it checks out a working copy. So you now got a working copy and a local branch that can be checked into. That points to a local copy of the remote branch, and that whole thing points to the remote server. The commands you use to get stuff back and forth are, once you've done the original clone, git fetch. And git fetch just says, go off to the server, get anything that's changed since I last looked, and shove it in my local copy of that server, so make my local copy up to date. Git pull is very similar to git fetch, but what it will also do is merge the changes from the origin branch into the branch, your local checked out branch. Now, the defaults, I think, for this have changed, whether it does all the branches or just the one you've got currently checked out. I think you can configure it or you can specify it when you do the command, just worth bearing that in mind. Going in the other direction, so I should point out when you do a git pull, if there are merge conflicts, if you've done stuff in your master and they've done stuff in their master, you're going to have to do a merge, you're going to have to fix those conflicts. And a pull is literally a fetch and a rebase just wrapped in one, a fetch and a merge wrapped in one command. So all the same things that you do with merge, you'll be doing with pull. If you want more control, you can do a fetch and then manually merge it, which has exactly the same effect. Push is in the opposite direction. Push will take your local commits to your current branch, push them into the origin one, and then push them onto the server. Again, if there are conflicts, it will be rejected, and you'll have to fix it and then try again. And this is the one where the default has definitely changed. It used to, by default, push all your branches, which could be really annoying if you've been fiddling around in the branch and forgotten all about it, and then you do a git push and it just shoves that onto the server. Now it just by default does the one you've currently got checked out. So that is remote repositories. There's an exercise which just uses two repositories on the same, well, it gets you to clone a directory on the same machine, so you don't have to have network access. I guess we're up to exercise 7 or something. Okay, so I mentioned before that Git supports sending patches by email if you don't have a direct link to the server. And that does it. You can do it by, you can create patches and mail them around. It does actually support sort of integration with Unix mailboxes. I've never actually tried doing that, but you can do it kind of manually anyway. So let's say we've got a change. So if we look at this, the bottom of those 2 lines of history says that origin master is one place behind where we are, and we want to generate a patch to send to the maintainer of this repository. So we say git format patch, and we tell it where we want to start from in the history, and it will create one patch for each commit from there up to where we currently are. In this case, there's only one of them, so it just creates a patch called 0001 and then the subject of the commit. This is one of the things where the subject blank line thing makes sense in the commit messages. And it creates a basically an email, which, so it's got from and subjects and things. The subject is the short line of the thing, and then it's got a diff embedded in a way that Git understands. At the other end, someone sends you a number of patches, and you say git am, which I think is apply mail or something, and you tell it, you can just give it, wildcards, tell it which patches to apply, and it just applies them as though it were a local commit. And there is an exercise for you to try it out. Okay, so we've kind of looked at how you can share changes between branches and between repositories. I thought I'd just briefly mention a couple of different techniques that teams use to sort of manage the kind of the sharing of changes. So the simple, well, not the simplest way, one kind of low-tech way is people could literally just push and pull amongst themselves. That could probably get quite chaotic quite quickly. Possibly you might have a hierarchy of maintainers. I think this is probably still the way the Linux kernel team work. So they have people, let's say there's Linus at the top who will accept changes from people he trusts, and they'll accept changes from people they trust who manage particular bits of the kernel. And it's all done, I think, with emails and patches and things. Apparently works fine. So yeah, sending patches around to each other. Way more common ever since GitHub was created is a central repo. It's kind of odd for something that's supposed to be decentralized. But it does make the workflows a lot easier, that you kind of say, well, everyone pushes up to this central place and then pulls back down again. That could be one repo. I mean, that's why we tend to work internally with our GitLab instance, where if a project just has a single repo, all the members of the team have commit access to that repo, and they just work it out amongst themselves. Or the more common model in open source on GitHub is, if you want to make a change to a project, you'll fork it, so you create a copy of it in your own GitHub account, you'll do the changes, and then you'll submit a pull request to the maintainer. If they like it, they'll merge it in from your fork. So that's how changes get shared about. In terms of master, generally is the kind of the main trunk version of a project, and there's different approaches for how to maintain the history on master. The simplest thing is just a nice simple linear history, as if it was Subversion or something. And the simplest way of doing that is literally all the commits go straight to master. If you make some local commits, you have to fetch and rebase and then push your changes on top. More commonly, you'd do a branch and then you'd rebase, you'd sort out the branch, and then eventually you'd get it onto master, and then you'd push your master up to the server. Another way we saw was the merge bubble thing. This is how a lot of things work when you're using merge requests. So you say, I've got a branch, I want to merge it into master. You create a merge request and people look at it, someone else in the team will say, yeah, that will make sense, or make these changes. And then when they're happy, they'll do a merge and they'll leave all the commits on the branch, but kind of merging back into master, so you can see the change that was there. No exercise for that section, so we'll move straight on to the next one, which is hooks. So getting back to that contents of that Git directory, .git directory, when you create a new project, there was a hooks subdirectory which I glossed over. That contains a whole bunch of sample hooks for various different lifecycle events that you can do things when they happen. Each of those files is executable, and it has an example of that kind of hook, and if you rename it and take the .sample off the end, then it'll immediately become active. So basically there's a certain number of file names that Git's looking for. If they exist, it'll run them as hooks, as long as they're executable. And they split into a few different categories. So there's the commit hooks. Pre-commit runs whenever you try and make a commit, and it gets to check various things about what you're committing. And like most of these hooks, you can choose to reject that thing. So you could have a commit hook that ran some kind of simple code style tests or something. You don't want it to be anything that takes a long time, because this is synchronous while you're committing, but or it could check the message or whatever. There's prepare commit message. That's useful if you want to auto-generate a message. So if you've done a git commit without saying -m, you've seen it come up in editor with a default message. You could use this hook to put something in that message. The commit message hook itself runs as it's about to do the commit and allows you to check and possibly modify the commit message. So if you've got rules about putting, starting with a bug report number or whatever it might be, or a feature ID, you can check those rules in that hook. And finally, post commit just runs afterwards. I don't think that one can reject it. That can just do anything that needs to happen, notifying people there's been a commit, something like that. There's similar ones for merging and rebasing. So there's the 2 pre-ones that run before allow you to check whether it's a valid thing to do and throw it out, and then there's one that runs afterwards just again to notify people. Exactly the same thing for patches. So all those ones I've mentioned previously run on the client. There's 3 that run on the server, so when you do a git push onto a server, these 3 hooks can run. Pre-receive is the one that runs before the whole push, so if you're pushing multiple branches, it'll run once, and it can go through and check everything and reject the push. Update is called once for each branch that you're pushing, so you can choose to reject a particular branch for some reason and let the others through. And post-receive is the one that just runs for notification whatever you want to do after it's happened. There are 3 other hooks that don't really fit in any neat categories. Post-checkout runs after you've checked out a branch or whatever, and that just allows you to do any setup that you might want to do. Post-rewrite, I think, happens after you've done something that changes history, which we'll see in a minute. And remember I mentioned garbage collection and the fact that Git just does it sometimes when it feels like it. Pre-auto GC is a hook that you can use to say, actually I don't want you to run this garbage collection. So there is an exercise, we're rapidly running out of time. With a couple of minutes have a quick look at the exercise, but I don't think we're going to get to the end of it. So I was going to talk a bit about rewriting history. I think I might have alluded to that briefly earlier on. First, a word of warning. This is where the dragons are. This is where you can actually lose stuff from because as soon as you start rewriting history, you're throwing away commits, which could cause problems. There's a few commands that allow you to change history. Some of you would have already seen git reset -- hard, I think, which basically says put my current position back to this point. So if you've failed a merge or a rebase or something, you can just say, right, throw everything away and go back to here. Git commit -- amend means commit some changes but merge them in with the last commit. So again, you're effectively throwing away the last commit and making a new one. Git rebase itself obviously rewrites history because you're creating new versions of the commits, potentially merge changes in. And then the big one is git rebase -i. And that's what the exercise for this section will be about, if you get time to do it. So git rebase -i is you basically say, right, I want to go back to this point, and then I'm going to run through all the commits from then and potentially change any of them. So you pick a point to start from, and it pops you into an editor, and you can see at the top under the command it lists, in this case, 3 commits. And then it tells you a bunch of commands you can use. So where it says, the default is pick, so it says pick this commit and just apply it as is. If you just exit that file in the editor, it'll just go through and it'll just apply the commits, there won't be any changes. Probably the least destructive one is reword. If you change pick to reword or R, then when you get to that commit, it stops and allows you to edit the message. Edit stops and lets you pretty much do whatever you like to that commit. So you can add other files, you can split it into 2 commits, whatever you want to do. If you pick squash, it takes that commit and squashes it with the previous one and lets you edit the message. Fix up is the same as that, only it uses so if you've just got one change that just fixed something you forgot to do in a previous commit, you can move those lines around, those list of commits at the top, and change them into different order. So you can imagine this can get you into a real mess, but it's also quite handy if you're working on a branch and you just want to tidy things up a bit before you push it. Once you've done all that, when you say git push, so at any time when you've rewritten history on a branch, if you try and push it, you're going to get this error that says failed to push some refs because you're behind the current one. Now, you can do that by saying git push -f, force, and it will literally throw everything onto the server and it will make the server's copy look like your local one. Don't do that if you've got other people who've checked that out. Almost never do it on master. If it's on a branch that only you were working on, or if only you and someone known person were working on, then talk to them and make sure they know, because when they do a get pull, it's going to cause trouble because you've now got 2 incompatible branches. So this is really something you should only do on a local branch that no one else cares about. As I said, there is an exercise to do that. We'll go back to that in a second once we've gone through the rest of the slides. I wanted to talk briefly about working with Subversion. We're supposed to use Subversion for everything, and I got into Git initially by using it as a front end to a Subversion repository. It allows you to do all the Git stuff we've just been playing with locally, and then when you're happy you can just push the changes and they'll go in as if they were Subversion commits, presumably if you've got them in a fairly linear fashion. To clone a Subversion repository into Git, it took me ages to get this set up. I couldn't remember for the life of me how to create a Subversion repository, but you do git svn clone instead of git clone. And the -s option means standard layout, so most Subversion repositories have a trunk, branches and tags directory. -s just means assume that, and it'll take the trunk and make that the master, and it'll take the tags and branches and turn them into git tags and git branches. You can do that with more fine-grained control, and you can tell it which directory contains each. So that checks out. It goes through and it basically walks all the way back through the Subversion history and creates a local Git repository with all the Subversion history. So this is quite handy if you want a local copy of a Subversion repository that you can play with, and it ends up much, much smaller than the equivalent Subversion repository. If you were then to do a git log, you'll see an extra thing in the log which is a git subversion ID, and that's just some magic that Git's using to try and sort of get the 2 things matched together. If you want to pull changes from Subversion into your local Git repo, you're on git svn rebase, which is kind of like a git pull with a rebase. And then once you've got all your changes on top of, because that basically leaves you with your changes on top of your copy of Subversion, allowing you to commit. And the command is git svn decommit rather than commit. I think commit diffs or something, and that kind of converts your Git commits into Subversion commits. I haven't used this for a long time. I'm not sure. It can go horribly wrong. It's not a good idea to do clever branching stuff in Git and then try and push it to Subversion, because it'll get in quite a mess, I think. But it is handy sometimes. So fixing mistakes. This is probably the most important bit, I guess. Things will go wrong. We've probably all had things go wrong on the exercise. There's a brilliant flow chart that at that URL. I'll send the slides out later. But my favourite bit of it is bit down here. It says, "Is anyone downstream? Yes. Are they enough to form a lynch mob? And if no, do you hate them?" And basically, in that case, it's fine. Just do an interactive rebase and just force push, and who cares? But it goes through all the different things that might be wrong and tells you what you can do. So just to summarise some of the things, if you've completely messed up something and you want to go back to the last commit and just throw away all your work, just git reset -hard. If you meant to commit something and you forgot, most common with that is if you do a git commit -a for commit -all and you don't realise you've got a new file and you didn't add it, then git commit -amend, I mentioned before, just does a commit and just squashes it into the previous one. If you made a commit and you've done something wrong and you just want to go back to where you were before you committed and fiddle around with it and commit it again, git reset one before head, or however far. The difference between git reset and git reset -hard is that git reset -hard actually points your head back to where that thing change was. Git reset takes you back there but leaves all the uncommitted changes so you can tweak them and recommit them. It makes more sense if you play with it, I think, rather than me trying to explain it. If you've made some changes and then you realise you need to go off and work on another branch or do something, but you don't want to lose them, but you don't want to commit them yet, then you can do a git stash. And the git stash is just kind of it's almost like a branch or a collection of branches that just kind of live off to one side. You can put as many things in the stash as you like and then pull them back out later. The simplest way is by doing git stash pop, which will just delete the last change off the stash and apply it to your working directory, but you can also pull them out one at a time. If you find a bug and you're not sure which commit introduced it, git bisect is really helpful. Haven't got time to go over it today, but you tell it the first commit when you know that thing was good, and the first commit when you know it was bad, and then it just goes halving it each time, and you run a test, and you just tell it whether that one's good or bad, and it will just zero in on the broken change. And if you've got a command you can run to do the test automatically, you can tell it that command, and it will just go and just do it in the background for you. If you want to rearrange stuff you've committed, ideally stuff you haven't pushed yet, then git rebase interactive we've already discussed. If you want to undo a commit that's already been pushed in a polite way that doesn't screw over all your colleagues, git revert. Git revert is not like subversion revert. Git revert takes a commit and creates like an anti-commit. So it creates a new commit which does the opposite of the one you're reverting. So you still have the full history, everything's still going forwards. It just undoes the changes. And finally, if you've lost some history, let's say you've deleted a branch or you've done a rebase and you've messed everything up, it's not actually gone. If you run git reflog, then that will list all the times when you moved away from a particular commit. So when we saw deleting a branch and it said was and then some char, that's because that's still there in the repo until you do a garbage collection. So if you've done a rebase and it's gone wrong, if you've deleted something, do a git reflog, find the right commit, which was the one that you didn't mean to delete, and just check it out again as a branch or whatever. That can be really useful. Anything that's committed in Git is generally safe. If you haven't committed it, then you can't necessarily get it back. So there was one more exercise about fixing stuff, and so it's now 4 o'clock, so I'll leave you to go off and do the exercises in your own time. Did anyone have any burning questions before we finish?